Okay, so welcome back. Today we're gonna continue working on the textbook of Rennie Introduction to Number Theory by what's the what's the name? Sorry, by Joseph H. Silverman. And last time we have already finished chapter three problems. So today we're gonna move on to chapter four, which is sums of higher powers and Fermat's last theorem. So in this chapter, is only a brief summary of what the title is going to be about. So we have already studied in last two chapters, chapter 2 and chapter 3, about the Pythagorean theorem, a squared plus b squared equals c squared. And of course, as a number theory course, we would like to focus on having positive integers for the variables a, b, and c respectively. Otherwise, we can just substitute anything. And of course, like in high school geometry, that if we don't set up any conditions for a, b, and c, then we can just pretty much throw in whatever we want to get infinitely many solutions with our setup. So again, chapter 2 and chapter 3 were both the Pythagorean theorem as well as Pythagorean triples, which gives the setup that a, b, and c are positive integers in this case. And now imagine, kind of wonder if we try to raise it to a higher power, such that instead of having a square, if we have a cube, meaning that we have a to a third power plus b to a third power equals c to a third power. Do we have any integer solutions? Now, in this case, we don't even limit it to positive integers. We can just assume to be non-zero integers, by the way, okay? And again, if we because if we assume that 0 is allowed, it will be very easy because we just need to set a or b to be 0. Then we have a and c being the same number, and then we will get infinitely many solutions. And this is not so interesting. So now we are trying to ask what happened if we keep almost the same condition. Okay, we can well, strictly we will have a, b, and c are all positive integers. Sometimes we might be able to include the negative integers, just not 0, for some situations, and see if we actually end up with solution sets for the equation a to higher power plus b to higher power equals c to a higher power. And of course, we're assuming the powers or the degree will always be the same. So we will have such as a to the third power plus b to the third power equals c to the third power, or a to the fourth power plus b to the fourth power equals c to the fourth power, but not something like a to the second power plus b to the third power equals c to the second power. Not like that yet. We want to keep the degree the same. So the material in this chapter is basically trying to give brief idea of how mathematicians actually studied it, and also how this relates to the Fermat's last theorem, which is state that for all positive integer n is greater than or equal to 3, there is no positive integer solutions a, b, and c such that a to the n power plus b to the n power equals c to the n power. Okay, so in this chapter, since it's a brief kind of like a brief summary or an introduction of this concept, there are not many problems actually we have only 2 problems, 1 and 2. Now however, we will try to skip problem 1. We will just briefly go through the question itself, but we will see kind of why we will just skip it right away. So question 1 says, write a 1 or 2 page biography on one or more of the following mathematicians. Be sure to describe their mathematical achievements, especially in number theory, and some details of their lives. Also include a paragraph putting them into an historical context by describing the times, scientifically, politically, socially, etc., during which they lived and worked. We have actually 26 options. Uh, Neil Abel, um, Cloud Gaspar, Bashir de Mezerica. Sorry, I'm not sure how to pronounce language the English correctly. Okay, and then C we have Richard Dedekind, uh, Diophantus of Alexandria, so on and so forth. We actually see like there are like, a lot of options there, but then here this problem is more like trying to do some quick research by picking mathematicians here, and then try to talk about their biography, okay, or uh, yeah, their past or what they have done, or contributions in math, as well as um, like historical content, like such as like the history during that era and how they connected back. Okay, um, so this is more like something that's not directly related to the calculations or math itself. It's more like focusing on the history of math. So I'm going to skip this part. So today we're gonna basically focus on the second problem of this chapter. And it looks like there's only one problem here, but in fact, it's developed into 5 parts. So hopefully, we'll be able to finish it by today. Okay. Um, by the way, if anyone is watching, you can notice that today I'm not using um, earphone here. So let me know if you guys cannot hear it clearly, because this is the first time I'm trying to do a stream without using it, and there's no microphone, other stuff besides my laptop. So if it's unclear or cannot hear at all, let me know, and then I'll try to fix the problem. In that case, I will just put my earphone back. Okay. um Okay, so let's move on to second problem. So the question says the equation a squared plus b squared equals c squared has lots of solutions in positive integers, which we actually studied in chapters 2 and 3. Okay, while the equation a to the third power, or I'll just say a cube, okay, plus b cube equals c cube, has no solutions in positive integers. Okay, now again, this is the reason why we want to give the limitation of a, b, and c to be integers. First of all, if it is non-integers, or more precisely any real numbers, of course we always can make it. We just need to solve it algebraically, like taking the square roots of again the variables that we're trying to solve by isolating it from everything else. Okay, and then take the cube rule, and then since we're if we're trying to deal with real numbers, of course we'll just get one root back, and we always can get one root. And if we are trying to do complex numbers, of course we'll just get 3 roots. Okay, exactly 3 roots, by the way. Now, of course, in that case, it will be not interesting at all, because it's not only that we have infinitely many solutions, but we can just generalize it to an expression, and then all we need to do is substitute it, and then and there's no pattern, like no obvious pattern of what that value is. Okay, it's not that interesting. So we want to study within integers. Now, again, we don't want to include 0, because once again, if we try to set one of them to be 0, then we'll be able to get the other 2 right away. For example, if we set A to be 0, then B will be equal to C. Okay, Or if we set b equals 0, of course a will be equal to c in this case, and then we'll just get infinitely many, and then it will not be interesting because we'll just get all the integers, and like there's no particular pattern that we need to look for. Or if we set c equals 0, then we'll have a is equal to negative b, so we'll just have 1 and negative 1, 2 and negative 2, so on and so forth, vice versa. And again, it will not be that interesting because it will just cover all the natural numbers or all the integers. Okay, therefore we are going to remove the the option of 0, and then more strictly we will just try to stay in positive integers, just like how we set up for the Pythagorean triples. Okay, now this exercise asks you to look for solutions to the equation a to the third power plus b to the third power equals c squared. Okay, so we're actually trying to twist it a little bit so that now instead of having no solutions that we actually know of, we're trying to see if we actually can get some solutions back. Okay, of course, in integers, c is greater than or equal to b, which is greater than or equal to a, which is greater than or equal to 1. And again, a and b in this case are playing the same role that you can try to switch the order, but then it's not going to affect the calculations. So by accident of choice, we'll just pick b to be the greater one. Okay, so part A, the solutions well, not hashtag the star has the solution a, b, c is equal to 2, 2 and 4. Okay, respectively. Find 3 more solutions in positive integers. And again, positive, not including 0. Okay. Hint, look for the solutions of the form a comma b comma c is equal to xz comma yz comma z squared. Not every choice of x, y, and z will work, of course. So you will need to figure out which ones do work. So what should we do in this case? Well, in this case, we can actually kind of start with some we can actually start with something like for example, here we're gonna do find 3 more solutions. So let's say solutions here. Okay, now what really matters here is that you might think it's not going to the z is not doing much here. We can just cancel the z, right? Unfortunately, no, because if we look at the equation itself, we have third power, and then a second power, meaning that let's do some quick stretch right here. Okay, by the hint, let a be equal to xz, b is equal to some yz, and c is equal to z squared. For some, again, because we want a, b, and c to be positive, we might as well just try to pick a, b, x, y, and z to be positive. Well, z definitely doesn't matter, but if z is negative, then we are forcing x and y to be negative. But in that case, we just might as well just choose them to be positive and then fix the z to be positive as well. Okay, for some x, y, and z be positive integers, then the equation, well, let me see, how should I say it? Well, we'll just copy it right away. Equation a cubed plus b cubed equals c squared becomes now we're gonna substitute in. So by substitution, a is gonna be xz, so we have xz to the third power plus b, which is yz to the third power, equals c, which is z squared, not equal to the third power anymore, but squared. Now, and if we try to simplify this, Okay, we of course will end up with x to the third power times z to the third power plus y to the third power times z to the third power, which is equal to z squared, which is z to the fourth power here. Okay, so this is the reason why we cannot really do we cannot just choose x, y, and z, but like in our simplification. And once again, this is what we actually would get. Um, in this case, if we try to do cancellation, we can cancel the z cube on each term, such that the first term turns into just x to the third power. The second term will become y to the third power, where the third term, instead of expecting to be z to the third power, it just becomes z to the first power, or z itself. Okay. So in this case, now we can actually try to pick something for x, y, and z. Okay, or in fact, we can just try to pick our x and y respectively, and then z will be dependent on x and y. So we can imagine z as a function with as a function of two variables x and y. Okay, and z is our dependent variable. Okay, so what we get is let me try to make it like this so that it looks a little bit easier to follow. Okay, we don't have to keep shifting it left and right. Okay, so once again, we can assume that A and B are the same. We can also assume that B and C are the same. Well, of course, in fact, we in this case, it's more important between the relationship of A and B. But then, if they can be the same, we can kind of assume that of course, x and y to be the same. Again, that is a linear proportion. So if b is greater than or equal to a, then substituting in, knowing that and the facts that by assumption that z is positive, then we can just divide both sides by z to get y is greater than or equal to x. So we can assume that y could be equal to x, but or greater than it. Now, if we choose x and y to be both 1, of course, because x and y are positive integers, okay, then substitute back to this new equation here. We have z is going to be equal to 1 to the third power, which is 1, plus 1 to the third power, which is also 1, which is equal to 2. Okay, then it means that we have x and y be equal to 1 and z equals 2. Then substitute back into our a, b, and c respectively. We'll end up with a is 2, b is 2, z is 4, which is the example that we already have. So we need to choose something else. So knowing the fact that y has to be greater than or equal to 1, greater than or equal to x, if we choose our x to be 1, so in this case, we can say we can say first case, if x is equal to 1, we cannot choose y equal to 1 anymore. We already know what the result is. So let's pick, let's say y equals 2. Okay. Well, in this case, and y equals 2. Okay. Then z, which is equal to x to the third power plus y to the third power, by the way. Okay, where x is 1, so x to the third power is 1, y is 2, so y to the third power is 2 cubed, which is 8. So altogether will be 1 plus 8, which is equal to 9. Okay, so we have z is equal to 9, implying that a is going to be equal to xz, which is equal to 1 times 9, which is 9. B is equal to yz, which is equal to 2 times 9, which is 18. And c is equal to z squared, which is equal to 9 squared, which is 81. Then we get A, B, and C respectively, 9, 18, 81, oh, not 31, 81 is a solution. Okay. Is a solution of the original equation. The solution of the original equation, which is like this. Let's see. Yep, I can type it this way. Good. So we actually found our first solution. Then, of course, we can just, how many do we need? Find 3 more, okay? So we can just choose something like, let's say if we have x is equal to 1 and y is equal to 3, then we have z is going to be equal to 1 to the third power is 1, 3 to the third power is 27, so 1 plus 27 is 28. We have z is equal to 28, implying that a is equal to, again, x times z, 1 times 28, which is 28. Then b is going to be equal to yz. Y is 3 times 28, which gives us 84. And c is going to be z squared. 28 squared is going to be, what is it? 784. Say 784. Okay. So we get 28, 84, and 784. Okay. We get, let me correct my grammar, as a solution of the original equation. And we can kind of notice that if we keep increasing the y, the z part is gonna get increased rapidly, by the way. So this time we can try to keep y to be 2, and since x has to be less than or equal to y, we already choose 1. So the other option that we have might be 2 in this case. Well, it's only 2, okay. Then in this case, it still satisfies our condition that y is greater than or equal to x. Okay. Then if we do that, we will actually get z is going to be equal to, again, x is 2 to the third power is 8, and then we have another 2 to the third power, which is 8. So we have 8 plus 8, which is 16. So we have z is equal to 16. And this is going to give us a, which is equal to x times z, 2 times 16, that's 32. B is going to be 32 as well, 2 times 16. And C is going to be 16 squared, which is 256. And, okay. So we get another solution, which is 32, 32, 256, okay, as a solution of the original equation. And therefore, we actually found 3 other solutions to finish this problem. There we go. Maybe I can just try to put it like this so that it will be easier to find out the 3 solutions. Good. You can find out quickly. So, part B. If A, B, and C, well, I don't know why they changed it to capital. Or I guess maybe they just want sort of isolate with the original problem. It is a solution to the original equation, and lowercase n here is any integer. Show that n square a, n square b, n square n cube c is also a solution to it. Well, let's finish the problem itself. We will say that a solution a, b, c, lowercase a, b, c to the original equation is primitive if it does not look like n square a, n square b, n cube c for any n greater than 2. Okay, so um, let me see. Now here is a reason why we want to exclude n equals 2 in this case. Of course, if n is 1, then there is no difference between a, b, and lowercase a, b, and c, which is actually reasonable. Now, why do you have to exclude n equals 2? Well, go back to part A. We see that one of the solutions we have is 2, 2, 4, right? Then we kind of need to exclude n equals 2 because of the algebraic reason that if we even if we substitute in let's say we have uh for example we if we substitute n equals 2 in it, we have 4a, 4b, and 8c as a solution. We still have a problem that the 4a, 4b, and 8c is a solution does not imply that a, b, and c is a solution. Okay, how do we see it? Well, we we just need to substitute back into uh, our first option 2, 2, and 4. Okay, but the detail I'll leave as an exercise and let you guys will figure it out. Okay, so we're gonna focus on this problem first. So again, this is more related to algebraic relations. Okay, we're gonna show that or prove that this is true. So okay, so what is gonna happen? Okay, suppose A, B, and C is a solution of the original equation loop. Okay, this means of course clearly we will have a to the third power plus b to the third power equals c to the second power. Okay, then if we replace, it's kind of like a substitution, but because we have something in common, meaning that we have the a with the capital A and capital A together. Okay, so we have to do a substitution, but we cannot say substitute because there's something well, the variable is we're using the same variable, but we're adding extra thing, kind of like uh when you have a function f of x equals something, whatever, and then we want to find out what happened for f of, let's say, x squared. Okay, we don't say substitute x equals x squared. It doesn't make sense because that looks like an equation that we actually can solve. Okay, so we will say replace x by x squared because we're using the same variable. Okay, so in this case we're going to we're gonna clarify in the same way. If we replace a, well, not x, a by n squared times a, and is it n squared? Yeah, n squared, and b by n squared b. Okay, so what we get is we have, or we obtain, whatever. I mean, they really mean the same thing. So on the left hand side of the equation is gonna be, instead of a to the third power, well, here, instead of a to the third power, we are going to get n squared a, capital A, to the third power. And similarly, b to the third power will turn into n squared b to the third power. Then after that, we're going to play the algebra. So n square a all together to the third power will become n squared to the third power times a to the third power, where n squared to the third power is just 2 times 3. Exponent rule. We're going to multiply the exponents, so it will be 2 times 3, which is 6, times a to the third power plus then we have n squared b raised to the third power. Again, we'll just get the same thing. We have something like this. Okay. We'll get something like this. Now, what does that do to it? Well, remember, we can now try to factor out something. Okay. What are we going to factor out? Well, we're going to factor out the n to the 6th power. This is going to give us n to the 6th power times the quantity a to the third power plus b to the third power. Now, in here, I'm going to factor one more thing, which is let's see, how am I supposed to say it? Which is n to the 6th power. I'm going to factor out as n squared to the third power. Right. So I'm going to write it this way. Times a raised to the third power plus b raised to the third power. Okay. So if we clear it out, we'll get something like this. Okay. Now keep in mind we want to set set the right we want to find out what we can replace the c by, right? Now here we still have the relation that a to the third power plus b to the third power equals c to c squared valid, meaning with this relation we're going to do a substitution quicken. Okay, so by substitution we will get n squared all raised to the third power. Third power. Sorry. Okay. Let's finish out. Okay. We will get c to the third power, like that. Okay. Oh, my bad. C squared. Again, that is because a cubed plus b cubed equals c squared, not c cubed. So we're doing a substitution using the valid relation that we have. Okay, so how is that going to help us? Well, now we kind of see that we have n squared to the third power, right? Maybe we can just switch it the other way around. Again, they're commutative, so we can write as n to the third power all squared. Okay, that's still valid as well. Okay, then we actually can get we can actually try to collect the c square the square, so we can take away the parentheses, and then we can see that we have something square times something square, right? We can now combine them back together. So in this case, we have n cubed times capital C all square. Okay. Then this means that yielding that replacing C by n cube c, which will be the right hand, which will give us what we have there, the final results, but after a replacement, uh, uh, will provide us uh, the solution. Again, we're just making a conclusion of what we actually got. Again, we replace the a by n squared a, and then we're going to replace the b by n squared b. And last but not least, we actually end up with n to the third power c as a replacement of c itself, being a solution. Okay, for us, the solution, well, should provide us that this replacement is a solution, is also a solution to the original equation. And there we go. We actually finish the proof. Okay. Now the second part is more like telling us an information of what how we define primitive. Okay, and again, it kind of makes sense that if n is greater than or is greater than or equal to 3, then of course it's not primitive because we actually can reduce it. We can also see that well, if n is greater than or equal to 3, then we can quickly do a substitution, and then we'll be able to see that the n is actually is possible to be cancelled, and providing us the results that a, b, and c will also be a solution. So meaning that the inverse will also be true as long as n is greater than or equal to 3. Okay, perfect. So now we're going to move on to part C. Part C, it says write down 4 different primitive solutions to the original equation. So it also says that is redo A using only primitive solutions. Okay. Now if we go back to part A, well, it's easier to going back this way. Okay. If we go back to part A, we see that between the first one, the first solutions that we chose is 9, 18, and 81. Okay. This actually satisfies n equals it actually satisfies as a non-primitive solution because we can choose n to be equal to 3. Then we have n squared as 9 and then n cubed is 27. We see that the first two values are multiples of 9, and the third value is multiple of 27. So in fact, we can actually reduce it so that we'll be able to get a primitive solution. Okay, so this is what we're trying to do in part C. So begin solution answer. I don't know. They say find write down 4 different solutions. Yeah. So from the solution 9, 18, 81, we have n equals 3 provided that. Now we're gonna write it like let's try to make another row then, so what are we gonna get? Well, we're going to have remember in the previous problem, it says if a, b, and c is a solution, then n squared a, n squared b, n cubed c is also a solution, and this is there's a bijection there for n is greater than or equal to 3. And since we have n here is equal to 3, which satisfies our condition, meaning that if we solve with the results n squared a, um, n squared b, n cubed c is a solution. We want to find a, b, and c. So what are we going to do? We're going to divide the first two values by n squared and divide the third value by n to the third power. So we're going to get fraction, the number that we saw was a 9, and then n squared, so we'll get 3 squared, and then the second value is 18 divided by, again, n squared, which is 3 squared, and then we have the last one is 81 divided by 3 n cubed, going to give us, oops, not this. We don't really need this. So first one is 9 over 3 squared, which is 9. 9 over 9 is 1. And then we have the second one is 18 over 9, which is 2. And then the third one is 81 over 27, which is 3. Is a solution using only primitive roots. Okay. Is a primitive solution of the original equation. Okay, like that. Now, it says 4 different primitive solutions, right? How about the given one, 2, 2, and 4? Well, in fact, if we try to include that, that will actually give us 4 different solutions, right? We actually found 3, and that one is the given one. Where the original one, the given one, notice that 2, 2, oops, 4. This itself is already a primitive solution, to whatever they like using the word to this or of this. It's just some grammatical yeah. Well, it's not really a mistake either using of and of to. But anyway, yeah, you know what I meant. This is a math. We're talking about math. We're not talking about we're not talking about. We're not focusing on about English grammar. So who cares? I mean, as long as we understand what we're saying, it should be good. Anyway, I'll also fix it. 2, 2, 2, 2, 2. So we actually get where are we? Yeah, we actually get this part here. The original example is already a primitive solution. Okay, and again, that is because we can already find an n that is greater than that's strictly greater than 2, right? The because 2 is if we want to pick some n which is greater than or equal to 3, then the first number is gonna if this original example is not a primitive solution, that means that we have to divide the first number, the first value by n squared, where n is greater than or equal to 3, meaning that n squared is going to be greater than or equal to 9. But if we do that, then after we divide by something that is greater than or equal to 9, this is definitely not going to give us any integer anymore, right? I mean, the factor of positive integer factors of 2 are just 1 and 2 respectively. So in order to keep it as an integer after dividing by n squared, the only option that we can choose is 1. But that's not going to satisfy the condition of not primitive, okay, non-primitive. So this is actually showing us that it is already a primitive solution here, okay. So we actually have that. Then we have the second solution, which is actually that. Third solution, we have Third solution is what did we put there? Let's see. It is right here. 28, 84, 784. Okay, these three. Now notice that so 28 can be divided into 7 times 2 squared. So uh, uh, in this case, we cannot really choose an n that is strictly greater than 2. I mean, the only option that we can choose is n is equal to 7. If we try, trying to pick some prime how do we call it, prime factors. But then if we choose that, then n squared is going to be equal to 7 squared, which is 49. Okay, we cannot reduce it anymore, because if we try to divide by 49, we won't even get an integer back. Okay, and of course we cannot choose n equals 2. Again, n equals 2 will work, but remember we said what is it, the ABC is primitive. For n is strictly greater than 2, not including 2. Therefore, this here is we will say that this solution is already a primitive solution to the original equation. Once again, we have spell miss. And last but not least, we can take the third solution here. Again, the solution 32, 256 is also already a primitive solution to the original equation. And again, 32 is 2 to the 5th power, 256 is 2 to the 8th power. And well, actually, no. This one is a little bit tricky. My bad. So this is not a primitive solution. Here's the reason why. We're saying that n has to be strictly greater than 2, but we never said that n has to be a prime number either. Meaning that we can actually choose a composite number, or even more crazy, we can actually choose 2 to the n power. So in this case, we can choose 2 to the 2nd power, or in this case, which is equal to 4, by the way. Then we actually see that from the solution, this, we have n is equal to 4, provided that, and here we go. So I'm going to copy this thing, and we're going to fix something. So instead of 9, we have 32 on top, and this one is B is also 32, and then the C value is 256. Oops. 256, like this. Where our n value is, instead of 3, we have 4. 4. And the 4 here. So let's do our calculation. Let's see. Let's recompile it and then see what we actually get. So the first one is, there's a typo here. I forgot a period or full stop in British English. Anyway, yeah, don't worry about the grammar or whatever. So for the last part, we end up with the first value turns into 4 squared is 16. So 32 divided by 16 is 2. And then 32 divided by 16 is 2 again. Then the last one, 256 divided by 4 to the 3rd power, where 4 to the 3rd power is 64. So we actually end up with 256 divided by 64, which is equal to 4, is a solution which we already found. Okay. So unfortunately, the last case is actually a repetition of the example that is originally given. So this does not count. Okay. Then in that case, what can we do? Well, let's see. In that case, we need to actually find a new one. Okay. So we have to ignore this part, or we actually have to remove it. Okay. So we're gonna find a new one. Let x be equal to 1. We're gonna stay with that again. Y in this case, we already use y equals 3. Have we? Let me see. Yeah, we use y equals 3 in our example here. So let's say if we choose y equals 3, but this time we have x equals 2. Okay, we're gonna keep it not too big. So we are going to let this for the setup in part A. Okay, then z is going to be equal to x to the third power, or 2 to the third power, which is 8, plus y to the third power, where y is 3, so 3 cubed is 27. So we have 8 plus 27, which gives us 35. Okay, implying that a equals, again, x times z, that's 2 times 35, that's going to give us 70. B is going to be 3 times 35, which is 105. And C, not X, C is going to be equal to 35 to 35 squared, which is 1,225. Good. Now notice that A, which is equal to 70, can be written as 2 to the first power times 5 to the first power times 7 to the first power. So we cannot pick any n besides n equals 1 in order to reduce it by dividing by n squared and keep it as an integer. Okay, so therefore 70, 105. This is a solution to the original equation. Notice that in this solution is primitive. Okay, so we actually get our fourth solution here, a primitive solution. Okay, and we finally finish this problem. Now we're at the second or last problem or part. Let's see, what do we get? It's asking that the solution 2 to 4 has a equals b. Find all primitive solutions that have a equals b. Okay, so what can we do? Well, we're going to do substitution, right? Because we already have the condition. Fine. So let's say solution here, okay, or answer. Again, it does not really matter. It's not going to affect that much. So given a equals b, we have a comma b equals a c. a primitive solution to, again, the original equation. That is a to the third power plus b to the third power equals c squared if and only if, well, we actually implies that this is going to be equal to c squared. And then this is saying that we have, because we have two copies, we can just combine them together like this. Okay. Now, is this the end of the problem or our solution? Well, let's put it down here. Okay, it's not, because it says find all primitive solutions that have this condition here, a equals b. Okay, then of course, if we usually see this kind of problem, finding all, either we're gonna give out. It's just like it's just like those competition problems. If we actually like, this is one of the things that is that's interesting in number theory. If we usually when we try to ask these problems, that actually, well, we should expect to have the answers already. If we usually ask find all solutions, usually we'll either end up with finitely many solutions, usually not too many, like 2, 3, 4, like not so much. Or if they are there are a lot of solutions, usually those solutions will be in some kind of pattern that we can actually make it into like finitely many classes. Okay, so if we try to continue working on this, well, we kind of need to go back to parts A and part B, sort of. Okay. Now notice that we want primitive solutions. Okay. So of course we will not expect well, we should expect that if we end up with A and C to be a solution, then n squared A, n squared A, and n cubed C is also a solution, right? I mean, that should make sense. But more importantly, go back to part A, we have the condition that we need to set our what well, we need to set our x and y and z, where x, y, z are actually having the kind of the relation there. Okay. Okay. So from part A, we also get A, which is equal to B in this case. So we're actually forcing that implying x is equal to y, first of all, which kind of makes sense, right? I mean, A and B are just xz and yz respectively, and z is is a positive integer, so we are dividing by non-zero. So there we have the cancellation to get x equals y. But and c is equal to z squared, where well, again, z squared, which is actually equal to x to the third power plus y to the third power, right? So I'm going to write it like this. Let's put it like solving equations. So we have c is equal to z squared, which by substitution we have z is going to be equal to x to the third power plus y to the third power. Don't forget the square outside. of course, which again is going to be replaced by uh once again x is equal to y, so we have x to the third power plus x to the third power, which is 2x to the third power, all squared. Okay. Now, how does that matter? We can try to take another one more step, which means that we can rewrite as something like this. Um, 4 times x to the 6th power. Okay, so we get something like this. Okay, where is it? Where is it? There we go. We have something like this. Now, again, what is a? Okay, a is xz, right? So, in fact, we actually can do a quick substitution here. Remember, xz can be, well, we actually can take a step like this. We need to keep some z here, so we can actually rewrite letter c in terms of a in this part. This part is a little bit tricky. So what can we do? Well, we can try to keep the one copy of z. Let's try to do it this way and see what's going to happen. So we in fact will end up with just we have something like this. So that is we have 2x squared times the letter a. Again, that's because we can take out one copy of x and then put it with sticking it with z, so we have xz, and then we can replace it by letter a. Why does it matter? Well, now we can actually kind of do a substitution back. Okay. So substitute this back to the substitute to the equation. Which one are we looking for? Well, the one that we haven't touched, 2a cubed equals c squared. Okay. We then have two a to the third power is going to be equal to what is it? 2x squared times a quantity squared. Okay. Which, of course, as we multiply out, we get 2 squared is 4, x squared is x to the 4th power times a squared, which is a squared. And then we can just simplify it. Divide 2a squared on both sides to get a is going to be equal to 2x to the 4th power. Something like that. Okay. Where in this case, where in this case our C is gonna be of course two how should I say that? C is gonna be equal to 2x squared A, right? Where C is gonna be equal to 2x squared A, and A we just solved it, which is equal to this. So multiplying everything, we still actually end up with something like this. X to the what is it? X to the 6th power. Okay. Not 6. Sorry, 4. 4x to the 6th power. So if x is equal to 1, then of course we just get our solution 2, 2, and 4. Okay. Now if x is equal to 2, okay, then we will not have a primitive solution. Notice that. If x equals 1, we get the example 2, 2, 4. If x equals to 2, we get well, if x equals to 2, then we can see that A and B are multiples of 4. 4 divides. Oops. Oh no. Okay. I kind of saved it. Divides A and B, and C is a multiple of 8. Actually, don't really need this here. Divides, well, C divides 8. Implying BC is not primitive. Okay. Actually, sorry, I made a mistake here. I couldn't say 4 because in this case, divide by 4 is saying that we're picking n is equal to 2. Okay. So let's try to do a quick calculation first to make sure that we're calculating correctly. Okay. If x equals to 2, then A is going to be equal to 2 times 16, which is 32. Okay. And then C is going to be equal to 4 times 2 to the 6th power. Again, that's actually giving us this. Then we have 64 actually. So I need to write down something like this so that we actually know what is going on. So what is our n value in this case? N is going to be equal to 4, so that we actually can see that A and B actually can be divided by n squared. Okay, and then C is going to be C is actually a multiple of n to the 3rd power. Okay, again, this is how we verified it. Then if x is greater than or equal to 3, then clearly x squared is a multiple. Well, no, it's not multiple. It's a divisor of A and B, and x to the 3rd power is a divisor of C, implying that A, B, C is not primitive. Therefore, the only, and again, what is the question asking? Okay, all the primitive solutions that have A equals B. Okay, the only primitive solution with A is equal to B is 2, 2, 2, oops, 2, and 4. Okay, well, to, again, the original equation, this is this. And therefore we actually get our final answer. And again, this actually kind of show that, like, wherever we have these kinds of problems, when it says asking finding all the solutions, usually what happened is that if we know that there is an answer of it, okay, if the question is not open, okay, some other people have already solved it, kind of like competition problems, okay, we expect that either we have finitely many solutions, most likely we'll actually get one or two solutions like this problem, or if there are infinitely many solutions, we should expect that there are some kind of patterns there that we will be able to make it into finitely many classes that we can kind of like make a have several patterns, not many, like maybe a couple of it, like two or three, for example, or maybe just one, and then like all the possible solutions will actually fall into one of those patterns. Okay, and that's what we can expect when we try to solve problems like this, especially for number theory problems. Okay, last but not least, we have the part E. Find a primitive solution to the original equation that has A is strictly greater than 1,000. Oh no, actually 10,000, not 1,000. So now we actually need to go back to what we have. Okay, notice that we have x x we have the condition that's, again, oops, so maybe we will get a solution here. Okay, we don't actually need to. So again, from part A, we have A is going to be equal to xz, B is going to be equal to yz, and C is going to be equal to z squared. This is what we get. Again, we can kind of ignore the the z part, because we can rewrite the z in terms of x and y. So in fact, we can actually replace it quickly to get A is equal to x times x cubed plus y cubed. B is going to be equal to y times x cubed plus y cubed. And C is just going to be the square of the quantity x cubed plus y cubed. Okay. Now, what do we want? We want our A to be greater than 10,000. Okay. So in this case, what can we choose? Well, we can actually kind of choose something like this. For A is, well, greater than this, we can pick, let's say A is going to be equal to this, which is going to be equal to 1 times 1 plus 10,000. Oh, not 1,000, 10,000. Okay. meaning that we can choose x equals 1 and then y equals 10,000. Okay. Now again, is this the only option we can choose? No, we can actually choose something even easier, such as, I don't know, maybe x equals 100, and then we can set our a to be like uh, uh well, again, keep in mind y has to be straight greater than x, well, greater than or equal to x in this case. If we choose something like x equals 1, x equals 10, then we need something like uh we need a y to be something like this. But in order to keep it easy, let's try x equals 1 and y equals 10,000. Hopefully this is going to give us something primitive, okay? Because the goal is having ABC to be a primitive solution. So we want to make sure that there's no n greater than, n greater than or equal to 3 that actually get all these three values reduced. So let's try something like this, okay? I'm going to choose this. Hence, now we obtain b is going to be equal to y times something very big. Of course, this is actually not a good option either, but why not? Well, we can try to get something not too hard to solve. So let's say if we choose, I don't know, maybe I'm not sure if that's a good option. Well, we can choose something not too big. Let's say, what can we choose? If we choose something like x equals 10, okay, then of course 10 cubed is just 1,000 already. Then of course we can choose whatever y positive, and then it will still give us the condition that a is going to be greater than 10,000, right? So let's say we are going to change our condition. Let's say if we're going to choose x equals 10, and then y is going to be equal to, again, we cannot choose y equals to x in this case. We, in the last example, last problem, we can't show that what happens if x and y are the same, okay? Which actually giving us a and b are the same. We will not get any primitive solution. So let's say if we're going to choose something like this, 1, okay? Then we actually will get 10 to the third power times 11 to the third power, okay? So is this going to be enough? I don't know. Maybe, I think it will be enough. So let's see what's going to happen. 10 to the third power is, of course, 1,000. 11 to the third power is 1331. So together it will be 2331 times 10, so it will be 23310. 23310. Okay. Then of course, in this case, our y will not be too big. And then we have x to the third power times y to the third power. Oh no, x to the third power plus y to the third power. And this is going to give us 23310 plus 2331 again, times 11, right? Then it's going to give us 25641. Okay. And then for z, for c is going to be equal to, what is it? Z squared. What is it? It's going to be equal to 2331 squared. Okay. which is, now I actually need a calculator. Let's check it quickly. Calculator. So we have 2, 3, 3, 1. Raise it to the second power. This is going to give us this number here. And again, this is something that we can already avoid. 3, 3, 5. Okay. Now, it is actually not that not that helpful if we actually multiply out. Okay. It's actually more important if we know how to factor it. And once again, there are a couple of things that we need to check. Well, first of all, we know that all of them are multiples of 9. Okay, how do we see it? Well, 2, 3, 3, 1, 0. This is what is it called? This is a multiple of 9 if we add all the digits together. Then of course 2, 3, 3. They're all multiples of 2, 3, 3, 1. 2, 3, 3, 1 is a multiple of 9. So we already says have n equals 3 for A and B. And then if we consider if we consider the square part for C, we of course have 9 squared, which is actually a multiple of 3 to the third power. So it's not going to work. So how should we do it? We have this condition here. So what shall we pick? Well, maybe we can pick something so that one of them actually contains how should I say it? Contains an let's pick an x value that's that is a multiple of 3, and then y value is not multiple of 3. Otherwise, we'll always be able to get something not so good. Okay. Or maybe we can just pick pick something like 11 and 13, something like that. We can give it a try. Let's say if we choose something like 5, we're going to reduce it. So we actually need a calculator here. Now again, this is why it's not that it's not that interesting if we multiply it, or it's not going to help us. Anyway, let's now we actually need to try to get something different. Let's see. So let's say we have 5 to the third power plus 11 to the third power, and then times 5. That's definitely not enough. So perhaps we need to try something like 5 to the third power plus 12 to the third power. This is still not enough. Well, if we keep pushing it, we probably will get something like, I don't know, let's say plus 14 to the third power. Well, these two are relatively prime. Hopefully this is going to work. Okay, times 5. Where's the multiplication sign? We get something like that, which actually satisfies. Okay. Or we have something like, for example, if we choose something like 9 to the third power plus 10 to the third power, and then multiply by 9, that's going to work as well. Well, let's see what's the smallest. Sometimes trying this is actually not that easy. Okay, that's not enough. So let's see if we try x equals 9 and y equals 10. Okay, let's see what we're going to get. And once again, 9 cube is 7. Is 7. What is it? 729. And then 10 cube is of course just 1,000. So we have, let's see, let's start over here. We have 1729 plus 1,000, which is 1,729 times 9. We have this. Maybe you can try something even smaller. let's say we have 7, okay, to a third power. I don't know what's going to happen though, by the way. This is going to be this plus 1,000, then multiplied by 7. I don't think it's going to work. Yeah, let's stick with 9 and 10 then. Or maybe something like, I don't know. Does anyone have any idea or any thoughts of it? Please share it if you want. So maybe we can try something like this plus I don't know, 13 squared to the third power times 6. Maybe 5 to the third power plus 13 to the third power times 5. We have something like that. Well, actually close enough. Maybe we can give it a try. So we have something like, for example, x equals 5. And then we have, what did we try? 13, 12? I think we tried 13, right? Maybe we can try 12 plus 12 to the third power. No, it's not going to work. It has to be 13. To here, we can pick something like x equals 5, y equals 13. Then we're going to get, here's a 5, here's a 5, here's a 13. And then this product here is going to be, well, it's going to be equal to 13 to the third power times 5, 11610. 11610, 11610. Again, which satisfies what we need, okay? Then, of course, we have here it's going to be 13, 5, 13. So let's see what we're going to get. We're going to get here divide by 4. Oops. Divide by 5 and then multiply by 13. We have this 301. Well, let me see. Oops, there's extra 0 here. 30186. 30186. And then here we're going to get 5 to the third power plus 13 to the third power, all squared. And again, multiplying it is not really the goal of what we're trying to do. So we just want to write as 2322 squared. And what we really need is actually the factorization of prime factorization of these well, A, B, and C respectively, so that we can make sure that we cannot pick n that is greater than or equal to 3. In this case, well, to be the factor that we actually need to divide by for A, B, and C respectively, not for n, but n squared and n squared, n squared, and n cubed respectively. So we now need to go here, Wolfram Alpha calculator. So we're going to throw in those values. So first of all, we have with prime factorization. So we're going to figure out what A is. We need to find out the prime factorization of all three values. So A is 11610. Copy it, share it. So Let's see. Hopefully, it can actually do prime factorization. There we go. So we have 2 times 3 to the third power times 5 times 43. So, okay. Now many wonder if the other two will actually be a multiple of 9 as well. So unfortunately, B and C are also multiples of 9. So this does not work. We'll just add the digits together. We can see that B is a multiple of 9, and then C, well, is actually multiples of 9 squared. Okay, so we might actually need to choose some other things then. Let's say uh, yeah, let's stick with whatever we start off. Let's say if we choose 10,001. This is going to be easy because, in fact, the reason why we actually keep getting multiples of 9 is because the x and y are actually ending up well, the difference of uh how should I say? Well, we choose the x and y, where in this case x plus y is actually a multiple of 3, which actually ends up with a multiple of 9. So if we try to choose something that we start off like initially, yeah, this is why doing math problems are actually sometimes interesting, but sometimes are actually annoying because uh we actually might not know the answers. So this is going to be this, and C is going to be equal to this, then square. This is going to give us this. Okay, let's try to fix our mistakes. Okay, so what is the prime factorization of 1001? This is the key. Why? Because 1001, in fact, it's not a prime, but the prime factorization is actually the next, the 3 consecutive primes, 7, 11, and 13. So excluding the first 3 primes, the next 3 primes product is going to be equal to that. And this is actually the key of what we now, if we try to write it down, we have prime factorization, 7 times 11 times 13. And of course, for C here, which is 7 squared times 11 squared times 13 squared. Okay. And then here we have 10,000, which is actually, well, not 10,000, 1,000, but you know what I'm saying. This is actually equal to 10 million and 1,000. So this here, if we try to do prime factorization, we have 2 to the third power times 5 to the third power. That gives us the last 3 zeros. And then times the 3 primes, 7, 11, 13. Okay. So we actually get these. Since there is no not exists an n that is greater than or equal to 3 such that n squared is a factor of 10,001, which is actually equal to a 10,001. the solution that we have, A, B, and C, B, which is this, and C, which is, in fact, we can actually try multiply O, okay? This is going to be equal to 1002,001, okay? 201 to the original equation is primitive. Okay, finally, finish the last problem. And that's it. We are actually done for this chapter. Okay, forget the first problem. Like we actually need to write out like a paragraph or actually a biography. That part we'll just do it whenever we have time. Okay, but for the rest of the rest of the problems, we actually finished it. So we actually have completed within 2 hours. Well, in one live stream, which is the first time we actually did it. I'm kind of amazed with myself too. But anyway, so we'll call it the end for the next chapter, chapter 5. Okay, which is about the visibility and greatest common divisor. We're going to start this chapter next time. Okay, let's see. We have 1, 2, 3, 4, 5, 6 problems. Hopefully, we can try to finish it and finish all the problems next time. Okay, and again, maximum hours 2 hours. If we cannot finish it next time, we'll just continue. We'll make another episode for it. Okay, so we'll call it the end of today. Thank you for watching. I'll see you guys next week.